Hello everyone, this is Philippe. I'm talking to you today from an airport. Unfortunately, there was a passing in my family and I have to attend a conference. Luckily, I had most of my slides ready. I'm recording them here, and hopefully, though I can't take questions live, if you have any questions, please feel free to reach out and hopefully we meet at the next conference. All right, let me get started. Today's talk is about studying and simulating discourse failures in interactive AI systems. So a little bit about me first. I'm a researcher at Microsoft Research. I'm based in New York, and I work at the intersection of NLP and HCI. If you go to my website, you'll find this research garden that I built that tells you a little bit about the different research direction that I'm going into. And today we'll focus on the purple branch here all the way on the left, specifically the Lost in Conversation paper and the user LM paper. I hope you find that interesting. Let me first start with a brief motivation for the work, and then we'll get into it. So I want you for a second to imagine that we live in a world pre-ChatGPT. Put a dinosaur there because it might feel like for some of you who are new to NLP that this is a long time ago, and I know some PhD students haven't lived in the pre-ChatGPT era, but it's not so long ago for us who have been in the field a little longer. But for a while in the community, there was this view that AI may not need to be interactive, that we could treat AI as a single step sort of black box, that if it was intelligent enough, it could kind of take in on the input everything that we know about the user and the task and the situation, perform the task, and then, you could basically at each turn of interaction treat the single step as the AI, and the overall interactive setup would just be the system on top of it. And I'm going to try to convince you, though perhaps this is a little easier these days, that AI needs to take the interaction with the user into account for it to be truly useful to the user. And some of the unique challenges that appear only in interactive settings with AI, a lot of them are related to discourse problems. But for instance, dealing with the absence of information, maybe because the user is revealing information gradually, or maybe because the user doesn't know certain pieces of information and therefore can't specify them. That leads to problems of having to resolve implicit dependencies, or for the system to have to learn to clarify when needed, but only when needed, right? And to do so in the right way. And you can imagine that that's not something that you have if you have an AI system that's not interactive, right? There's degradations due to long context that occur in long interactive sessions, or compounding errors in long horizon. There's of course imperfections because if you're dealing with real users in real systems, there's a lot of noise that appears. And then there's more complicated problems that maybe some of you have heard of, like sycophancy or manipulation or persuasiveness of these systems in interactive settings, etc. But what I want to point out here is that a lot of these problems relate to discourse issues. And I think specifically that discourse issues, they sort of compound in the interactive system. So if you had, issues of resolving dependencies in a single turn setting, imagine how much more difficult it is in multi-turn. If you had difficulty having to figure out, those specific nature of content, it becomes harder in the interactive setting as well. Okay, so hopefully this motivates the work and why I think working on discourse and working on interactive settings is intertwined in some way. And now I'll move to presenting to you one of the recent papers that I've worked on, which is called Lost in Conversation. This work was a collaboration between a couple of us at Microsoft Research and then a couple of people at Salesforce Research. And let me get started. So for this work, I'll try to motivate it as well a little bit so you understand where we came from. This is Hiro and me, who are the two lead authors on this paper. Around the late 2024, we started talking about PL benchmarks, programming language benchmarks. You've probably heard of SWE-bench. You've probably heard of human eval. At the time, I hadn't. Hiro happens to be an expert on this topic, so as we were having conversations, he was telling me that a lot of the benchmarks were saturated. The funny thing is, these days, the benchmarks still feel saturated, though the names of the benchmarks have changed. So in some ways, this is a perennial issue. And I asked, okay, what is human eval? And so if you don't know, then you're going to learn with me here. This is an actual sample from human eval. Human eval is a data set from OpenAI that they released some time ago. And it contains about 100 or 150 samples like this. The sample reads something like this. You have to write a Python function. The Python function should be called below 0, take in a list of ints as operations, and produce a Boolean. You're given a list of deposit and withdrawal operations on a bank account that starts with 0 balance. Your task is to detect if at any point the balance falls below 0. If so, you should return true, and otherwise you should return false. And then there's a couple of examples. And a question for you briefly here to think about is, what do you think is wrong with this sample? Okay, so if you are like me and Hero, you might come up with two different reasons. The AI perspective is more that perhaps this task is too simple. Real coding tasks are much more complex, especially today, right? We can expect AI systems to do much more complex things than just building simple Python functions that can probably be done in 10 lines of code. But the HCI perspective on this, the human-centered perspective, is that actually nobody really writes prompts this way. And so even if the model can solve this and get 90% accuracy at these kinds of tasks, it's not reflective of real users and how they would prompt. So based on this, Hero and I went into ChatGPT at the time and started playing around with how we would actually prompt. Imagine for a second that we needed this function. How would we actually go about and do it in ChatGPT as real users? And we came up with this idea of sharding the instruction. So you can see here on the left and the right. On the left, the blue one is the original instruction from human eval, and on the right is the sharded equivalent. The sharded instruction has exactly the same information, but it's been split into pieces, which we call shards. So the shards here, there are 6 of them, and they each reveal smaller amounts of information. So for instance, the first shard says, I want you to write a Python function. It's called this, and it needs to find out, the main logic if accounts are ever negative. Then the second shard is like, by the way, the inputs is a list of ints that represent transaction amounts. And then the third is, oh, by the way, you can assume that the initial balance is 0. And then the fourth one specifies the output, right? You should return true if it's negative at some point or false otherwise. And then the examples are folded in as extra shards. And we went on a bit of a sharding expedition. We took these high quality benchmarks that existed around the time, both programming language and natural language tasks like summarization. These are all generative tasks. And we went and we took instructions and sharded the instructions. And the nice thing here is that since these benchmarks were, well established, we could repurpose the way that they did evaluation. So for instance, human eval comes with these unit tests, and so for each instruction that we have, sharded or otherwise, we can repurpose these unit tests to do this gold standard evaluation. Okay, so now that we have a sharded instruction, we're going to use it to simulate multi-turn conversations that are going to be underspecified. And the idea is quite simple, though the diagram is a little complicated. At each turn, there's going to be a small LLM that's a user simulator that's going to reveal at most one shard. We use an LLM here because we don't want to reveal a random shard, but imagine, for instance, that that the assistant has just asked a clarification question. We want the LLM, the user simulator LLM, to figure out, okay, which shard should I reveal next here that's most natural in the conversation so far. At each turn, the assistant can then attempt an answer or not. If it attempts an answer, then it is evaluated, and if it's correct, the conversation ends, and we give the reward to the assistant. Otherwise, if for instance it hedged, or it asked a clarification question, or it refused to perform the task because it's missing information, then we go to the next turn where the user simulator keeps going, right? And the conversation ends, as I said, either if the assistant has produced the correct answer, or if all the shards have been revealed, and we get to the end and the assistant has still not solved the task. So this is a version of a diagram that tells you the difference between full and sharded. So the fully specified single turn setting, which we saw in blue, is the original. We reveal all the information at once in the first turn, whereas the sharded multi-turn setting, we first split the instruction into these smaller blocks we call shards, and then we reveal at most one shard at a time based on a user simulator. And you might have this question in your mind of, you see where we're going here. We're going to say that the sharded multi-turn setting is much harder for assistant models than the fully specified single turn. But you might be thinking, hey, maybe this is because the process is lossy, that when you perform this sharding process, you lost some information and you made this sort of sharded multi-turn setting infeasible. Right? And because of that, we added this concept of the concat experiment. So going back to the diagram earlier, you can see this notion of concat experiment. We take the sharded instruction and we concatenate it together in a bullet point form where we say, okay, now perform this task. Here's everything we know about this task, and we give all the shards at once in the first turn, in a bullet point form. And so the difference between concat and full is the paraphrasing that has occurred during sharding, but they're still both single turn. And then the difference between concat and sharded is that the difference between single and multi-turn, but the commonality is that they use exactly the same word, right? So now hopefully you can have this kind of nice baseline that if full and concat performance are similar, that means the sharding process was not lossy. It maintained the same level of information. But if there's a gap between concat and sharded, that means the reason the models are getting worse is not because of the rephrasing, but because of the multi-turn nature of the interaction. So here's where we get to kind of the main results of this paper. It's a large table, and I don't expect you to look at all the numbers, but sort of look at it, visually. So here, this is the models that we had tried at the time. You can see one model per row here. It's listed from the smallest, oldest models to sort of like the state of the art at the time. And then the columns, you can see, for instance, here's the first third here on the left is how the models perform on the 6 tasks that we have in the experiment in the fully specified setting. Then in the middle is how they perform in the concat setting, and then on the right how they perform in the sharded setting. And the background color here indicates how much of a drop it is from full to either concat or sharded. And what you can see is that on average, there's little drop in the concat setting, particularly when you look at the pretty good models. The older and smaller models are affected a little more, perhaps because they've been overfit a little bit on the fully specified instructions. But if you see here all the way on the right, at the average ratio across the 6 tasks of concat to full, you can see that most models are in the 95 to 100% range, meaning their performance is very, very similar. The ratio of performance between concat and full is very close to 100%. On the other hand, you can see this big red that occurs in the sharded setting, and you can see that the ratio from sharded to full is typically 55% to 60%, meaning that there is an average degradation across these 6 tasks of around 35 to 40% across all of these models when you do the same tasks, but you do them either fully specified and in a single turn versus doing them in this underspecified sharded multi-turn simulation. So long story short, models perform much worse in the sharded setting, and they perform similarly in the concat and full setting, like we expected. Okay, so now we get into a little bit more depth as to why do the models get lost in conversation. So in order to study this, what we did is, for each of the settings, for each of the instructions we have, we simulated not 1, but 10 different simulations to observe the variations that occur in simulation. And the idea that we have is that there is, 3 metrics we can measure here. First, we can measure average performance. So if you run 10 simulation for a given instruction, on average, how many times did you solve the task? And what I showed you a couple of slides ago, the big table, was average performance. Then I can define 2 new metrics. First, I can define aptitude, which is the best case performance. So imagine I ran 10 simulations. I can say, how often did I at least solve it once, the 90th percentile? And then on reliability measures the difference between the best case and worst case. So, the difference between the 90th percentile and 10th percentile for a given instruction across the 10 simulations that we do. So what that means is, if I've solved this task at least once, how often do I solve it at least 9 times? And what this is measuring, is if the model never solves the task, then that's okay, that's reliable in not solving the task. On the other hand, if the model can solve the task sometimes, it should be able to solve it reliably in order to have low unreliability. Okay. So what we want to understand is when we move from single turn to multi-turn, what is causing this? Is it a loss in aptitude, meaning like some of the tasks have become impossible even in best case performance in multi-turn, or is it an increase in unreliability, meaning the model still has the same aptitude boundary, it can still do the tasks, most of them the same in single and multi-turn, it's just that the likelihood that it fails has increased in the multi-turn. So essentially what we find is that there is a very large increase in unreliability when we move from single turn to multi-turn and a small drop in aptitude. Let me show you how to interpret that result from the graph here on the left. If you first focus on the full and concat settings here at the first two rows, you can see that we've put models from left to right, from least performant to highest performant. And what you'll observe is as the models get on average better, so if you look at the median, you'll notice that the models are getting better, they are moving up, but also that the average unreliability is shrinking, meaning the bar plots are getting narrower and narrower. And that means that the worst case and best case performance are sort of narrowing. So same thing with concat. So in single turn settings, as models gain aptitude, they also reduce in unreliability. On the other hand, if you look at the third row here and the sharded, what you can see is that from left to right, models are getting better on average, especially the best case performance. You can see it goes from 50 to 74 for some of the models. But what you can see is that the unreliability is not decreasing. So the height of each of the box plots, which is the difference between best case and worst case performance, is sort of stuck around 50%. And this is why we coined this phrase, like, when LLMs take a wrong turn in conversation, they get lost and do not recover. What we mean by that is that it's not just that the models are losing in aptitude, like certain tasks that they can do in single turn, they can't do in multi-turn. It's that in the multi-turn setting, if at any point the model takes a wrong turn in the conversation, right, and makes a wrong assumption or misunderstands something, then it will likely get lost and not recover. On the other hand, if you simulate enough times, as long as there is one path where it makes no mistakes at every turn and is able to kind of keep track of things, then it's able to succeed. So that's the reason why the gap between between aptitude, which is best case, and the worst case performance, which measures unreliability, stays large in the multi-turn setting. Okay. Now going to secondary experiments, you might be thinking like, but you're testing raw LLMs here. What about agents? So what if I had sort of like a scaffold on top of my LLM to maybe keep track of memory or maybe repeat information that's important from the user or summarize it, etc. And so this is why we added actually two experiments that are fairly basic, but represent what you could imagine an agentic setup doing in a multi-turn setting. So we have recap and snowball. They're quite simple. Recap, what it does is, you run a regular sharded simulation where you reveal one shard at a time. And then at the very end, once all the shards have been revealed, you add an additional turn, which is essentially a concat, where you say, okay, just to recap here, here's all the information the user has said, and the assistant essentially gets one more try at the task, right? And you could imagine that if you provided all in the last turn, perhaps the performance would be similar to concat. Snowball is essentially a gradual version of recap, where at each turn, including intermediaries, you also remind the assistant, by the way, here's what the user has said in previous turns. So that at each turn, you essentially give all the information that the user has said so far. And what you can see here on the right is that, the 4.0 mini and 4.0, which we tested at the time, they do a little bit better in the recap and snowball setting. They do better than sharded, but they don't quite close the gap and perform as well as the single turn settings. So it helps a little, but it doesn't fundamentally solve the problem. And perhaps this is a little bit philosophical, but we argue that, multi-turn capabilities in models should be baked into the model so that the model is able to approach the multi-turn context intelligently, rather than sort of adding an agentic framework on top of it, which is sort of tape if the model is not able to process multi-turn ambiguity properly. Okay, and then we had some other analyses based on the logs of the large-scale simulation that we performed. We found that, the earlier the model attempts a full answer at the question without full evidence, the more likely it is to degrade and not produce a correct answer. If instead, in conversations where it's able to refrain from performing full solutions by either working with the user on partial solutions, or asking clarification questions, or refusing to answer until certain information is provided, the models tend to do better. And one thing that I'll end here with in part one is that, we believe that sharding here is the bottleneck. Perhaps as you saw the way that Hira and I were proposing to shard, you were thinking, hey, is this really how a user would speak? And even so, is this really how a diverse population of users would speak? Because when we think of interactive settings, we shouldn't think narrowly. We should think, okay, like there's all sorts of ways that people, interact with AI systems, and we should model that as part of the process. And also, I would say that we overfocus on one specific phenomenon in user simulation here, which is underspecification. And it's an important phenomenon because we found that in 40% of conversation in a large-scale analysis of Bing chat logs, some form of underspecification occurs, but there are many other phenomena of user communication that we need to model in order to understand the performance of AI systems in interactive settings. And just for fun, I'm kind of presenting to you some other papers, some of which I'm not involved in, that I think have also taken this route of simulating a specific user behavior of interest, and building a framework, just like we did with sharding, around something that they care about in how users behave. So for instance, this great paper from KAIST, Discover LLM, which presents this idea of, okay, maybe users gradually themselves discover their intent, and it's hierarchical, and they built a framework that's more complex than ours on how to simulate that sort of behavior. Like you say, okay, I want a poem that includes an animal, actually I want the pet, or actually I want a cat, right, or something like this, and you gradually have the user reveal its perspective. Or this work from NYU around simulating human memory. So we all know that humans, we don't have perfect memory and we forget things. And in long, interaction, we don't have perfect recall of what the AI system said, both because we didn't necessarily read all of it, or even if we read it because we forgot. So they did this whole paper around how do we get a user simulator to have imperfect memory, right? And how do we add that into the simulation? There's also this work currently submitted to YAM-NLP, I believe, that I found interesting. So this paper focuses on, simulating users that have different expertise levels, all the way from novice to intermediary to users that have great expertise in a topic that they're having a conversation with AI about. And finally, this other paper that I'm involved in, led by Jihoon, focuses on situating the task as part of a longer chain of tasks that a user is doing. For instance, when users potentially switch the task that they're working on or revise the task that they're working on, and creating these much more dynamic scenarios that happen in our narrow, just underspecified setting. Okay. But now what I want to invite you to think about is if we care about all of these behaviors, we can't really simulate them independently, right? Ideally, we want to simulate user behavior in a more end-to-end way. And since we're at ACL, I'm going to kind of propose to you that we should simulate users using a language model. Now, okay, this sounds pretty nerdy. Let's see what we mean by that. Okay, so this is work that was led by Tarek, who was an intern at MSR with us last summer. He did this great work that got published at ICLR called Flipping the Dialogue, Training and Evaluating User Language Models. So here, what we're trying to do is imagine we want to simulate a user in a conversation with AI, trying to perform a specific task. So for instance, in this example, imagine a user trying to get information about strategies on how to lose weight and the impact of certain drugs and medications on weight gain. So the way most of the community does this is by doing sort of simulation through a prompted LLM, an assistant model. So you might take your favorite LLM and then tell it, okay, you must act as a real user. You must should potentially make typos, and you should, be rude if you need to, etc. Like you're a real user, you're not an assistant, and perform this task. So we did this with, like our favorite GPT, Claude, and Gemini models, and here's the kind of first utterance that they produce. Hey, looking for tips on losing weight, plus how certain meds drugs affect weight gain, like antidepressants. Any info? And you can see here that Opus and Gemini produce similar questions, and they all start with hey, which is kind of interesting because hey is not that common. People don't really say hey to their AI assistants. And this is actually a task that somebody did in wild chat, a large-scale data set that was recorded of people interacting in the wild with AI systems. And here's what the first interaction that the user actually had with the AI system. The real user just said, does allergene cause weight gain, right? Which is much more brief and to the point and more aligned with what you expect a person to say in ChatGPT. And what we want to point out here is that there's this assumption that the assistant role of the language model can perform any task, including simulating any sort of behavior. But actually, these models have been fine-tuned narrowly to be assistants, right? And that makes them poor user simulators. This is what we show in this paper. And instead, what we argue is that we want to train models that are specific to the use of simulating users, and we call these models user language models. So we'll first go over the procedure that we followed to train a user language model, and then we'll talk about what we did with it. So how did we train the user simulator? So we took a large corpus of in the wild user assistant conversations. We basically took wild chat, right? And you have N conversations in there. Some of them are multi-turn, some of them are not. And for instance, here conversation 1 is the same one from the example earlier. And then we used an LLM to extract what we call the task intent, right? What is the user trying to do in this whole conversation? This is what will be the input to the user simulator, right? So getting information about strategies to lose weight, that's the task intent. So we extract that with an LLM. And we have one for each of the conversation in our corpus. And then from there, we are able to create training samples to train a model specifically to produce user utterances given a task intent. So on the first turn, what the user's LM sees is just the task intent, and it has to produce the first utterance, right? Because the user is in charge of starting the conversation in a user AI interaction. From there, the assistant might reply, and then for turn 2, the user LM has to, given the task intent and how the first turn went, the user and assistant produce what the start of the second turn is, etc. And until the conversation ends. So once the conversation has ended, the model has to produce an end of conversation token. And that's because user simulation, not only does the user have to decide what the first turn is, they also have to decide when the conversation ends. That means they don't send a follow-up into the chat. So we created a large-scale version of this data set. We took wild chat, which has about 1 million conversations in it, and we filtered it down aggressively and deduplicated and focused on English at first. And we got out of that around 300 to 400,000 conversations. We generated the intents with GPT-4o, and we trained 2 different models here to produce these, next turn utterances, one at the 1B scale and one at the 8B scale. And some additional details here. And what we saw is that, first, like the model that we trained in this way achieves much lower distributional alignment to the human utterances. So what we do is, we train on a set of users, and we hold out users that are never seen during training. And we see how likely would we be, to produce the utterances of these users. And this is measured in NLP with perplexity, which is like exponentiated log probability. And what we can see is that our model achieves much lower, perplexity on held out users' utterances, both with intent conditioning and without intent conditioning, compared to assistant models. We also showed that not only can we generalize to other users in wild chat, we also generalize to users that were collected in a different paper called PRISM, which is like, done by other researchers with a different user population, meaning that this model seems to have learned a little bit more in a general way how users speak. Okay, but perplexity only gets you so far. So then from there, we did what we first call this intrinsic evaluation. So because user language models were a new concept, we had to come up with new metrics in order to evaluate how these user language models perform. So specifically, we created a total of 6 metrics. The first 3 focus on the level of diversity that occurs in the first turn, given a task intent, the ability of the model to decompose the intent across multiple turns, and the capability of the model to terminate the conversation when it should be terminated. And what we find is that, assistant models are really terrible at decomposing the intent. They try to put everything in the first turn, and they're also really terrible at ending the conversation. And if you think about it, that's normal because assistant models are not trained to end conversation. They always respond to a user query, right? And so that's why you can see that even GPT-4o, which is a much larger model than what we tried, has very low F1 on ending turns, which is a hard task, but we do much better with our user LM. Okay. The next 3 metrics that we had, one relates to naturalness. So does the simulator pass AI detection, specifically here pangram? So the interesting thing is, though if you ask GPT-4o to act like a user and talk like a user, AI detectors are still detecting that as AI generated text. On the other hand, the user LM models pass for user written text, which is a sign that they've distributionally aligned a little bit more with how users speak, right? And then we had these robustness checks for in a adversarial setting, does the user simulator stick with its user role, or does it fold back to being an assistant? We found that we do much better on that. And then does it stick with the intent that it was provided, even if you tell it, okay, like let's work on a different task from the assistant, like we expect the user to lead the conversation and to be in charge. And so we can see that the user LM is much more robust than if you just prompt an assistant model to behave like a user. That's a much thinner veneer, and as soon as any adversariality happens, you land back into an assistant model essentially. Okay, but intrinsic evaluation is sort of like limited in its capacity since we built the metrics ourselves. So we then performed an extrinsic evaluation, which connects back to the first part of this talk. We essentially took the tasks in Lost in Conversation, and instead of sharding manually, now we have this user simulator that can sort of do this dynamic sharding. We can provide the task on the input, and we can see how the user simulator just talks one turn at a time, which was the objective here. So we took these 65 tasks from the math and the Python domain in Lost in Conversation, and then we compare simulating the conversation with user LM versus with the prompted GPT-4o and GPT-4o mini model, which is kind of the more standard practice. Okay, so just to show you an example, so the user intent might be something like, okay, write a Python function. This is from human eval, like we saw. Given an array of integers, you have to sort them between 1 and 9 inclusive. You have to reverse the array and replace digits by their name, 1, 2, 3, etc. And if you look on the left here, this is 3 conversations simulated with GPT-4o. And what you'll notice is that though they look a little bit different on the surface level, they are very, very similar. So the order in which information appears, the wording that is used, and the number of shards is always 4 here. So turn digits into a name, into names in a list. Start with a list of numbers. Start by having a list of numbers, right? And then like you can see, like if they're between 1 and 9, we want numbers from 1 and 9. If they're between 1 and 9, etc. Right? So those wordings are very similar. So you're kind of feeling like you're simulating potentially one user, but it's a very kind of homogeneous single type of user, right? On the other hand, if you look here on the right, you'll notice that there is a lot more diversity that occurs in user LM. So for instance, one thing that I can point you to is it says keep only the integers between 1 and 9 in the first conversation here in the second term. And then here it doesn't say keep, it says sort the numbers between 1 and 9. And in the third conversation it says ignore any number that is not in 1 and 9. So it has kind of used negation here, right? And then it says reverse the list in one case, or like now add sorting into it, which is kind of an indirect way of saying this, or sort those kept numbers, right? And then even at the end here, you can see, like here it says translate the remaining digits into its English name. English name is correct, but it was not in the original instruction here. Or like replace each digit with its corresponding name. or like translate the remaining with its capitalized English name, right? So you can see here, like there's sort of like more lexical and sort of like semantic diversity in how the information is produced, as well as the ordering of information is shifted a little bit more in this example. And so we ran these simulations, and that's what we kind of like studied then through metrics. So the first thing that we see is that the three simulators, they reveal about as much of the original task intent, with user-LM revealing a little bit less, but sort of that's not statistically significant. Like they mostly reveal about the same amount of information from the task intent, which is a good sign. Then there is more information diversity. The user LM will introduce more nuances. It'll add specific demands that are unique and not in the original task. Like for instance, the English name that we saw in the example, it might skip more often the non-required information that is sort of implicitly or sort of obvious, and it might repeat information more often. It will have much higher pace diversity, meaning the number of turns. So the number of turns in a given conversation might, range from 2 to 7 with user LM, but it's like, for instance, with GPT-4o Mini or GPT-4o, in a much narrower band of 4 to 5, right? And perhaps, you could play around with the prompts in order to increase diversity, but this is something that occurs naturally with user LM because the model was trained on, the diverse corpus of conversations. And then the lexical diversity, which I kind of explained with the example earlier, we see that there's much more unigram differences from one sampled conversation to the next, even given the same task intent. So the user LM uses much more varied phrasing with each request, which all of this diversity leads for the assistant model on the other side to perform much worse on these tasks. So what we find is that when you simulate with a benign sort of like GPT-4o model, then the assistant on the other side has an easy time, right? Because it's very narrow, the information is revealed always in the same order, right? On the other hand, against user LM, the assistant performs much worse, right? And we kind of argue like this is more realistic and represents how user AI conversations would occur in the wild for these given tasks. Okay, so assistants struggle to handle user nuances in multi-turn settings, and the user LM covers the necessary information of the task, but the nuances it introduces due to the sampling that occurs in a language model causes assistants to fail more often. Okay, so that's it. The user LM model is on Hugging Face. The Lost in Conversation code is on GitHub. If you're interested, I haven't put the links, but it should be easy to find. If you have any questions, please feel free to reach out. I wish I was in the room with you so I could take questions, but unfortunately, that's not the case. If any of you are in NYC at some point, please let me know. We have a wonderful Microsoft Research office, and I'm happy to invite you over and have a chat. And yeah, that's it for me. Thank you very much for listening and the patience. I hope the recording was high enough quality. And take care, everyone.